A small bag of sand is released from an ascending hot air balloon whose constant upward velocity is v0 equals 22.75 meters per second. Knowing that at the time of release, the balloon was 80.8 meters above the ground, determine the time tau it takes for the bag to reach the ground from the moment of its release using g equals 9.81 meters per second squared. As always, I think the best way to start a problem is to draw a picture. So here is our hot air balloon with the little basket, and then over here is the sandbag. And the key thing is that the hot air balloon starts off with speed v0, which means so does the sandbag. But then the sandbag, of course, goes up and falls down until at some point it hits the ground. They tell us that the initial height, I'm going to call h, they tell us that initial height is 80.5. And they tell us the initial speed is 2.75 meters per second. And of course they tell us g, and they tell us the non-standard value of g, but that's just a sampling quirk. So let's bring this a little closer. So that's our height. Get our color coding correct. And what we would like to know is if the time starts at 0 when the bag is released, then what is the total time of flight when the bag hits the ground, splat down here. All right, so we're looking for let's take our variables and put them into some sort of order. So we start at t equals 0. T initial is 0, right? And t final is unknown and desired. And our original position is the height. Here I'm using y instead of x because we're moving vertically instead of horizontally. It doesn't really change anything, but in the second unit it's more useful because we will have x and y vary separately. And then we end at some final position, which is 0, because I'm going to put my origin right here, right where the bag's about to hit, and call that plus. Also, keep in mind, I have drawn it moving over like this, but it just goes up and comes down. It's just hard to draw things like that. So imagine this whole path was over here and then came down like that. Right. Which means that we end, the bag starts at height h, right here, and then goes up, and then hits the ground at 0. You can put the origin anywhere you want. Generally, the lowest point that you know something's going to get to is going to be the safest. It makes as much as possible positive. All right, then we have the velocity, and our original velocity is v0, which is given, and our final velocity I'm going to call vf as this thing hits the ground, but I don't know what it is, and I'm not asked for it. And then finally, during the motion, once the bag has been released, the only thing acting on is the Earth, so it has an acceleration which is like this. And so our acceleration is magnitude g, but points down. And that takes our chart together. Generally, solving a kinematic problem, what we want to do now is say, what equations relate things that we know to the thing that we're looking for? And if we look here, we're looking for TF. So we want to use an equation that has T in it. So we can plug in T equals TF into that equation. But we don't have VF, so we want to avoid an equation that has V. So as a quick reminder, what are these equations? Well, we know that V is VI plus AT at all times, and also that Y is YI plus VI, T plus 1/2 AT squared. Again, remember here I'm using Y instead of X, but it doesn't change anything. And then finally, V squared is VI squared plus 2A times the change in position. Having said that, now we look here and we say, well, but this has a VI in it, or VF in it, which we don't have. And so does this one. So these two equations end up being not particularly useful. The one that we're going to want to use is going to be this one. Okay, having cleaned up the page a little bit, got rid of the scratch work, moved the equation over here, moved A up here because it was in the way. We are going to use this equation, and we're going to throw in the values that we know. So I'm going to say the height was, we end at 0, and we started at 80.8 meters. Our initial speed was 2.75 meters per second times the time, which is what we're looking for. In this case, the time of flight. And then we'd have plus 1/2 times, we know the acceleration is minus 9.81 meters per second square, and then times the time squared. And without any kind of nightmare or anything, that is just a quadratic equation. So you solve it any way that you solve quadratic equations. Most likely, it's not going to factor. Physics things don't tend to end up being factorable. Real world numbers don't behave nicely. You could complete the square if you wanted to show off your math chops. You could use a quadratic equation. You could use a quadratic solver on your calculator. You could even do it graphically. And in fact, that's the one I'm going to do. All right, I'm going to do it in Desmos, do it graphically like I just did here. Couple of important things. Whenever you do Desmos for me, I tell you don't do a screenshot, do a graph export, and I've broken that rule. But I've broken that rule because I wanted you to see the equation I typed in, which is just the equation for y that we had in terms of t. I also did this little cute Desmos trick, which maybe you know how it or not, but I said, hey, plot only for positive t, because it doesn't make sense for negative t for our problem. So that cuts off, that's why there's no equivalent thing over here in the graph. And we can see a couple of things. We see that the thing does in fact rise a tiny bit before falling all the way down to the ground. It's a little weird to have that very tiny initial velocity when clearly the dominant thing is going to be just falling. But, you know, sapling's weird. And then over here, I said find where this function crosses the axis. Because remember that when it hits the ground, y equals 0. And I'm going to find the time that that's the case. And by clicking on it, I got that point generated. And we can see that the time it hits is at 4.349 seconds. The actual sapling answer that they gave us was 4.35 seconds. So we can see that we agree within sig figs. Again, you could do this by quadratic formula or by quadratic solver. That's perfectly fine too. I just wanted to do it graphically to show how to do that. And again, the actual numbers are the least important part of this problem. It's setting it up and getting to the equation that you could solve to get this answer. So there we are.